So Chris, let's start it off. What is LabVIEW 2010 all about?
LabVIEW 2010 is all about time. In addition to the typical feature in a new version designed to help you develop code faster or easier, LabVIEW 2010 will flat out make your code run faster.
So, obviously everyone in this audience is excited about that. So you're telling us that we can just take our existing code, open it in LabVIEW 2010, and it's automatically going to run faster?
Well, don't take our word for it, John. Let's just show you. Here, we're using some standard LabVIEW primitives to multiply and add to a large array. I'm going to run this exact same code in LabVIEW 2009 and in LabVIEW 2010. As you can see, we get a staggering 3.5x improvement. This shows how computationally bound code runs faster in LabVIEW 2010, and that means you get to leave work early and just go home.
This graph shows the performance speedup of several applications in our test suites. You can see that there's a wide spectrum of how code can be affected by compiler optimizations. Obviously, the speedup you'll see in your applications will depend on what your code is doing. Compiler optimizations can affect operations such as DLL calls or UI calls or I/O-bound applications. While portions of your LabVIEW code may speed up more, our benchmarks have shown that your overall application should see a runtime improvement up to around 20%.
Well, that sounds impressive. I think this audience in the LabVIEW community is always interested in higher performance of their code. Can you guys tell us a little about how you made this possible?
The compiler was one of the primary focuses of the 2010 release of LabVIEW. Although we've continuously innovated in the compiler with enhancements such as in-placeness and clumping, we wanted to provide a compiler that could optimize the LabVIEW code you write for runtime performance, regardless of how well optimized the G code is written. This slide shows the compile chain in LabVIEW 8.6. LabVIEW 2009 introduced defer, a high-level intermediate representation that is graphical in nature and preserves LabVIEW execution semantics such as parallelism and data flow. LabVIEW 2010 introduces a second intermediate representation using LLVM. LLVM is a high-performance, open-source compiler infrastructure that is widely used in both academia and industry. It's been used at companies such as Apple, Adobe, and Google, for example. LLVM uses a very low-level intermediate representation and possesses knowledge of target machine characteristics such as SSE instructions.
NI Compact DAC has served as one of the easiest ways to make voltage, digital, and sensor measurements using an external PC bus. Until now, multi-slot chassis only came with a USB interface. But today, we're pleased to announce a new 8-slot Compact DAC chassis with gigabit Ethernet. The full set of C-Series I/O modules are supported. An Ethernet chassis is programmed the same way as a USB chassis. In fact, for the majority of Compact DAC systems, you can simply move your modules over and use your exact same software. This new technology allows the user to see and configure their network devices directly from a web browser. From here, you can modify your IP address, set up security settings, and even rename the device, all without having to install a driver. You can see the recorded sound from the two channels on these charts. You can see as the waveform travels between two microphones, the pattern actually repeats. At the muzzle, you experienced about 154 dB, but by the time it got to the ear, it was 143 dB.
In response to an overwhelming number of requests, we're pleased this year to introduce the NI PXIe 5630, industry's first PXI vector network analyzer. Optimized for automated test, this module delivers fast, flexible, and accurate network analysis in a compact 2-slot PXI module. So now with PXI RF instrumentation, you can characterize a full range of RF components, including antennas, filters, power dividers, amplifiers, brains. All right, here we have a bandpass filter connected to the PXIe 5630 to perform these precise phase, magnitude, and impedance measurements. Now we're talking accuracies of tenths of a dB in magnitude as well as tenths of a degree in phase. Now if we take a little closer look at the magnitude response of the filter, we can see that with a PXI vector signal analyzer, it's a very good solution for many applications, including performing nonlinear measurements. In blue, we can see the uncorrected response using the PXI VNA. And then by applying a user calibration that we performed this morning for this unique test setup, we can see the highly calibrated as well as highly accurate measurements shown in green.
The NI embedded vision system in the back of our demo uses 2 cameras to follow the dart on its path to the target. Because both systems are tightly synchronized using NI time sync, we can easily measure the speed.
All right, are we ready? Go for it.
Our team thinks big, and we had this wind turbine blade in mind, but we were told pretty quickly to find a way to scale back our full-scale test. So we've got these model turbine blades, not response on the 3D picture control up here.
We're performing a static analysis by simultaneously.
The CDAC chassis is connected to a Windows laptop, which is using LabVIEW web services to publish the measurements to the network. If I give a beer to a friend, but forget to close the door, the temperature is going to rise and my beer is going to get warm. That would be a catastrophe.
Needs a recliner, and could we pull up that ESPN 3D?
Its Blu-ray players to analyze its 3D video quality. Now, John, while you're getting your glass.
Well, that sounds like some impressive performance. So we're testing this 3D Blu-ray player.
We've got an actual setup here in hardware. Why don't you explain this demo?
So this is how it works. We have one chassis representing the base station with 2 channels, the spectrum plot and the constellation plot on the top. And basically this constellation